Hi, my name is Justin Berrier, and for the engineering design class 496A, I have decided to continue building the tennis racket stringer for the midterm. For this, I have this project. I'm recording it using Cam Studio, which can be found at camstudio.org. As you see here, assembly is complete. From the proposal, I decided to add decals, which I have. This is a mechanical tennis racket stringer from Gamma. And as you can see, I add some decals on the outside. In addition, I updated the materials for this turntable bar you see right here. I found online that it was made up of chrome steel, so I applied that. And a couple other materials, applied new materials too. And then the rest of them, I just kept what they were when I did it for the midterm. In addition, I added a tooth and gear assembly, which was proposed for the final report. Let me hide these components. As you see here, there's the gear, and the tooth is right there. And up in there, there's a black piece which prevents the tooth from going in the wrong direction. Let me see if I can get this moving for you. As the tension bar rotates, you can see the gear moving with the tension bar, and the tooth stays placed because they are not relative to each other in movement and rotation. And in addition to these assemblies here, I cut down on the actual parts by using sub-assemblies. Let me show you. This one is the tooth and gear and hand knob assembly. As you can see, it has a tooth here. The gear is included into a sub-assembly. This is tension bar sub-assembly. It has all the struts, nuts, bolts required to hold it together. A hex screw inside there, hold the weight. And then this tension bar was attached to a winder stand, which includes its bearings and all its stuff, the screws, and all these other parts, which when I created a full racket stringer, cut down a lot of the processing time. And this is just a support post. There's two of them. I added all the clamps on it, and when I go back to the tennis stringer, you can see all these components as some assemblies put together and made this one big assembly. Some parts like the feet, they're just added right onto the major assembly, and everything now having, like I said before, its screws. There are hex screws here, many screws all over the place. In addition, all the mates were made as they would in real life. Some of the parts, like this turntable, are able to move, and the support posts on top of them move in and out. These brackets move up and down in order to clamp the tennis racket in place. The winder stand is able to translate back and forth, and as before, the tension bar goes up and down in order to apply the correct tension, as with these the string clamps, the blue ones. It moves with its own sub-assembly, and this is, if you remember the tooth, this is what controls the movement of the tooth and locks it in place on the gear, and the gear is attached to the tension bar. For collision, Pretty much tooth and gear are the main problem. Let me show you. In blue, you'll be able to see the tooth is being stopped by the gear every time they come in contact, and that's because it requires a sophisticated mate in order to make the tooth move up into it, rotate up in its slot so they can lock into a new place on the gear, and I just couldn't figure that one out. So I just left it as a collision. Now, there's multiple drawings used for this project. Let's see, where's the first one? Made a 3-view with an isometric picture. This was the large end cap, one of the parts where the string will be gripped, so when you apply the correct tension, the string doesn't fly out. Made proper dimensions. When you're in part drawing, you can use your own dimensions, or you can use a dimension expert, and I ran into problems with that because it would overlay on my own dimensions, so I just kept mine and had enough so you could determine how to make the part. In addition, I made numerous detail drawings, since there were so many small parts on big parts. As you can see here, this is the wheel, which has the tooth assembly on it, but this is just the gap part, not including the tooth. And as you see here, I enlarged it to show you all the dimensions of the stopping bar for the tooth, the rotation room, and up here I show you more dimensions from a different angle, another detailed view. And use section views. Right here, this eyepiece, it shows the middle section. As you can see right here, since the part is angled, there's material coming off, and I wanted to show that in a section view for those who couldn't visualize it. And then I just show some quick dimensions. Top view, just show the whole part's not in an angle. And then I use some cropping here in order to better show you where I cut this section view out. In addition, I use broken out section views. Not this one. One more back. This one. Alright, broken out section views. This drum, which is used to attach to the tension bar, there's holes within it in order to this hose hold onto the tension bar, and then this one so you can grip onto the assembly, the bearing assembly, in order to rotate on the winder stand shaft. And I use broken out sections to show you how deep these holes will go in and quick dimensions. Up here are 2 broken out views using splines. This should show you from a top angle view perspective what is going on. For this one, I showed some alternate positions for the tension bar. Here's the winder stand and tension bar in tension. Here's at rest, and then I show an exploded view, all the little parts and screws. And since the tension bar was really long, I used a brake right here in order to cut down on the overall size so you could see it better. And I just showing our detailed view of this region right here, region A, so you can see the components for the tooth and gear. For some assembly drawings, I use multiple configurations. This one's showing 90-degree, like if you're doing the head or the bottom of the top or the bottom of the head of the racket, you'd want it in this configuration. And over here on the right, if you're doing one of the sides of the head of the racket, you're stringing the frame, one of the gommets, which is where the gommet's a hole where the string goes through. This is the configuration that you would have. And And down here I just show some alternate positions using these configurations to get a better realization. It's a little simple. And in addition, I use this assembly drawing to show some differences in appearances. These colors on the right, the yellow represent which move in unison, and the blue represents which subassembly moves in unison. Like I said before, the tension bar moves with the shaft and the winder stand, and then this finger gripper base over here, the cyan color, moves on its own. It has a tooth which locks in for the gear on tension bar assembly. And then I use some display states. In this drawing I've gotten rid of the end caps so I can show you the tooth and gear assembly, and I just label them with respective colors on which parts move in unison. For the simulation part of the project, I used this tension bar. Set up the study, I had gotten rid of multiple parts. Got rid of these two drop weights, and in addition the actual knob that holds them in place, and the cap, and the support hex screw, because whenever I ran the simulation it would fail, and I think it was because of too many parts it was trying to mesh and simulate for. So once I did that, I came in, I made a fixture. Since when your tooth is locked in place with a gear, overall the shaft is locked in place, so I kept the middle portion fixed, because this is where the shaft will be locked in place. And I use 59 pounds in my tennis rackets, so I added a 59-pound force, simulating that in a simple manner. The force is just going to be normal from this tension bar and perpendicular to the ground. So in this view, just expect the bar was pretty much horizontal like this, so the force is going down to the ground. And once you get to that tension, you would tie off the string. But anyways, for the simulation, I did that, ran it, I meshed it, and it came up with stresses, displacements, and strains. And just like I would expect, the most stress occurred at the end joint of the tension bar, where it connects in place. And with the 59 pounds of force displacement, of course, the moment arm, it occurs most at the end. And you actually can see this once you maximize the weight on the tension bar in real life. It says here 1 inch, and well, that's not totally realistic, but in real life you actually can see a bending motion going on, but it still holds up. And for the strain, yeah, makes sense. Down here in the drum, most of the strain is going to occur at the shaft and any other stress concentration points. And SolidWorks did pretty good because it's green, meaning that the part should hold up, which is realistic because I've maximized the weight on my bar and it never broke. For some software limitations, when initially it was create assembly, I found out that you can't move a part that is fixed, and after finding out that you have to go and say this property manager component, and you just gotta make it flexible. And sometimes I would make things invisible, or parts would no longer be made together, and I don't know why. So I just tinkered around, found which ones made flexible and still worked. That's how I solved that problem. Another one was simulation. My computer only has 2 gigabytes of RAM, So many times I'd be running a simulation, especially when I started with all the other parts that had just hid for you. They said resources of your computer was getting low, and then the study would crash. So I, limit up all the part components. And in addition, it failed many times for some odd reason. I don't know. So I went into the properties of the run, and I just used large displacement. It had compute free body forces before. Got rid of that, and it worked. So that's about it. A tennis racket stringer. Yeah, it pretty much simulates what it would be in real life. The results show that the part will not fail under the 59 pounds force I gave it. Most tennis rackets, the maximum is 90 pounds for more control, and if you want more power, you lessen up the force, the tension force on the string, so you get more of elasticity, so you get more springy action, gives you more power. And I use 59 pounds, which is a nice little in-between measure, so you get both control and power off your racket. Well, that's it. Hope you liked it.